everybody. Thank you for coming to this talk by Professor Amza. It's my pleasure to welcome today Professor Amza. Professor Amza received a bachelor degree of engineering from the Bucharest University and a master and PhD degree from Rice University in 1997 and 2003 respectively. His research areas is in the area of distributed and parallel systems. He joined the computer engineering department of Toronto University in 2003 and as an assistant professor, and since 2009 he serves as an associate professor at the same department. Today he's going to talk about anomaly detection on computer servers in cloud. I find the subject extremely interesting and very trendy, and I hope that everybody will find it the same interesting as I do. Thank you, Professor Amza, for being with us today. We are ready to start with your talk.
Thank you so much, Professor Petrakis. Thank you, everyone, for hosting me. I'm really glad to be here introducing our work on Semantic-Aware Anomaly Detection for data centers and clouds. This is work I supervise at the University of Toronto. So everyone knows about clouds. I'm hoping data centers, right? They are key buzzwords in the recent past. And ideally, like Tom Cruise here, anomaly detection would be so simple as touching some screens and pulling some data and drawing and zooming in, and in a couple of minutes you found the problem. Unfortunately, this is not how it is, and in the real world, what we have is vast amounts of data, what we are calling big data, which is data for logging, so text logging, and data for monitoring these often large systems. So why is this the state of the art? Well, traditionally, these systems, the large distributed systems, were fault tolerant, so designed for fault tolerance, designed to mask failures. So if a failure happens, then the system is supposed to automatically cover it up. So failure masking is expected. The system is supposed to do failover automatically without triggering any alarms or anything like that. And because obviously we want to know if a failure happened or not, the system behind the scenes is generating log data and monitoring information for the user to later on look at and figure out what has happened. Because this data is very large, the process is still user bound, so the user is still the bottleneck in such a process, because like I said, the information that is generated is very, very large. So let's take it one by one. So first, logging in large scale systems. What do we log? So we log detailed information, like I said, for calls, for network activity, for control flow, for errors, for warnings. And this is being logged for distributed systems of the size of thousands of servers. So you may have heard of these, some of these distributed systems. So Hadoop, Cassandra, HBase are currently freeware that people can install, use, build our clouds on. And for example, a 1,000 node Cassandra cluster can generate 24 terabytes of log data per day. So this definitely very big data. This data is complex. There are interdependencies in the data. For example, this is a file system call graph. So like I said, oftentimes calls are being logged. And here is a visualization of the call graph from an ext3 file system. And we can see that the bad calls, so the calls with errors, have been depicted in red. So there are here 37 errors out of 188 calls. System monitoring is also another source of big data. So in this slide, I'm showing some time series for data monitoring the system. For example, we can plot data for CPU usage, for memory usage, for total page cache, for CPI, so cycles per instruction. And you can plot this kind of data all day long, and you can plot all sorts of other types of data. And for all of this data that I'm listing here, suppose we were monitoring for a Cassandra cluster, same size as before, 1000 node cluster, at a rate of 0.1 samples per second, then we would get about 2 terabytes of this kind of data per day. And normally, there's not a user sort of sitting there looking at the screens to see this time series. Normally, again, this data would go on file, and nobody's actually looking at it. So let's recap what we have so far. So why do we do this logging and monitoring? Why do we collect this vast amount of data? So we do want to understand the root cause of certain anomalies. So this is called root cause analysis. And like we said, in logging, we typically log the type of information pertaining to the call graph of the system, the execution flow of the system. And for monitoring, we perhaps want to look into things like resource interference, resource bottlenecks, memory leaks, and those kind of things. Okay? So from both of these type of information, which is vast, we might determine what is wrong, if something is wrong with the system and the particular application. So our key idea in this context is to do some type of semi-automated or automated anomaly detection. And again, the idea is to monitor and classify these huge amounts of data per some type of context. So if we just have the terabytes of data, it's very hard for the user to actually take a look at it and figure out what has gone wrong. But if we classify per semantic context, then it's both easier for the machine to classify and for the user to look at what has happened, again, with some kind of semantic information. So after we do the classification, we build the anomaly detection information into statistical models, and those models are built on the fly, and suppose the models are accurate and complete, after the models are built, we can use the model to filter out normal data, which does not need to be logged anymore. And we will discuss what normal is. And we can also do high accuracy anomaly detection based on the model, because the model can predict what is normal and what is not. And overall, we can reduce the storage and performance overheads that otherwise would be incurred in systems doing this logging and monitoring all the time. So our techniques are two, and I will mostly focus on the first one and give you some highlights of the second one. And in the face-to-face talks, I can answer questions about either. So these are both automatic techniques for anomaly detection. They are for logs on one hand and for monitoring information, system information on the other hand. And we call them, the first one is called Program-Aware Detection of Anomaly, so PAAD, fancy. And the second one is for resource monitoring. We call it Semantic-Aware Resource Anomaly Detection, so SARAD, which apparently means something in Hindu, which I don't know. So the first one, the PAAD, the Program-Aware Detection of Anomaly. Let's go back to logs. So this one is about logs, about textual logs. So let's take a look at what a log looks like. And you see it here. Okay. So this is a module, program module, which let's say is doing a file transfer. Okay. So a small snippet of program doing a file transfer. And you see that it has log statements inserted in the program at certain points. So you see L1, L2, L3, L4, the log statements. And okay, And these log statements are supposed to tell us the control flow in the program, so the execution path of the program. So for example, in this case, you see L1 is the starting statement, which says we're going to send file A over here. And then we may loop around in this part of the program, sending one block at a time of these files. So sending block 1, 2, etc., looping around, printing L2. And then finally, if the whole file was sent, we will have this statement, send file A, as L4. And the information in the log also allows us to capture the duration of this program. So you see the timestamps here in the logs. This is each log statement, and from the beginning to the end, we can compute the duration of the program. So these logs actually contain detailed information about the execution flow and duration of our program. They also contain situations and error statements when the execution flow led to an anomalous behavior. So in this case, we're assuming that after L2, we went to this L3, which is failed to send the file. Okay? So this is an abnormal program path, execution path, leading to an error. And finally, we can have a normal path, so just like before, where we actually end with sending the file, but this duration is much more than the usual one. So this, in principle, is all in the files. Okay? This information is all in the files. However, all we have is the actual textual file with just this. So we have the timestamps and the statements. Okay? And if we encounter an error like this, okay, then it's actually quite difficult to determine this graph that I showed here. And let's see why. Okay, so inferring the execution from the log, textual log per se, is not as easy as I made it sound. So in the ideal world, we look, we figure it out. But in the real world, it's actually not easy at all, and there are challenges for determining what actually went wrong. So there are 3 challenges, and we'll go one by one and explain what happens. First, it is really hard to identify what actual tasks executed from the logs. Okay? So you may have seen that I told you it's about the file transfer, but in the log there was no such information. Second, it is hard for us to distinguish between normal and anomalous, and I'll tell you why. It seems easy because there should be an error statement there, but in reality it's not that easy. And third, there are overheads such as storage and processing overhead which prevent us from doing this properly. So let's take the first challenge and understand exactly what's going on. So here we're showing the log file that I showed you before. So this is a log file. However, what goes into this log file are prints from many, many threads. So here I'm showing one anomalous and one normal thread, and they are both printing to this file. And typically there's no identification for me to understand which statement comes from which thread. They're all interleaved in this one file. Second, the server runs forever in a while loop. And so, I will have like the terabyte file with these interspersed statements. And there's thread reuse. So once a thread finishes one task, then they are allocated another. And so basically I'm just staring at the terabyte file of these kind of things. Second challenge, there's actually no baseline. So when I'm starting to look at the terabyte file, assuming I could, there's no baseline. I don't actually know what I'm looking for. Anomalies do not always generate an error or a warning. So imagine you're stuck in an infinite loop. There may be no clear warning. It could be a bug, and you may not reach the nice error statement that was put there. Okay, so how do I identify what is normal versus what is anomalous if I do not have the error or warning? And finally, what I've been mentioning all along is that these print statements generate a lot of overhead. So typically in the past, log messages were designed for the human to read. But nowadays, like I said, very few people actually look at the terabyte file. I mean, just imagine opening it in Emacs or right, your favorite editor. You don't do that, right? So verbose logging, which is the type of logging I've been assuming so far, generates 2,600, a factor of 2,600 times more information than the production level logging that is normally used in practice. So that is called info level logging. So basically info level is the default logging, which generates very, very little information. In fact, just the start, maybe if you're lucky, start and end, not all the sent or those kind of things. And if we say, okay, forget the user, let's just do automatic text processing, regular expression matching, text processing itself is very expensive and it's often imprecise. So our key observation is, like I said, back to how do we capture the context? And the context is really those task names that I started with. And we notice that many server codes actually are very modular. So they do have certain tasks that execute over and over, and those tasks have certain names, and we call those module stages. Okay, we could call them phases. Later on, actually, we'll call them phases. It doesn't matter what name we use, as long as we are somewhat program aware. So program aware, we know the names of these stages or phases. Our method, which is Program-Aware Anomaly Detection, is an on-the-fly method. Okay, so it's real-time, on-the-fly, with low overhead, very lightweight, and almost completely automated. In fact, we are making it completely automated right now, and I will tell you where we are at later on. So, like I said, the server code, including Cassandra or HBase or any of the codes that you see, have a modular structure with some functions, some methods called over and over again. In this case, I'm assuming some random ones like foobar, bus. And we call these stages. And each of the stages, as you can see, is executed in any given point in time by multiple threads. So this is blown up here. So the same barcode is executed by many tasks from many threads. And each of those tasks, like I said before, has those log statements inserted in the code. And so we can trace the execution of each task by looking at the log statements that it executed. For example, task 4 executed L1, L3, and task 6 executed L1, L3 again, and task 5 executed L1, L2, L3. Okay? So the key point here is that there are many, many threads, hundreds of threads, executing the same code at the same time, concurrently, on many nodes. So we can capture the execution flow from the log points on the fly without generating logs. Because there are hundreds of them, we have some statistical confidence to understand what is normal or usual versus unusual. Okay? And we can exploit this similarity between the task code, between many threads executing the same task code, in order for us to build a statistical model that is somewhat reliable quite quickly. So we do this, like I said, through statistical anomaly detection, and let's summarize what we have so far in the PRADA method, so Program-Aware Anomaly Detection. We leverage the fact that the code has staged structure or modular. We have a way of capturing the start and end of each task. We log the statement as trace points without spitting them out on the log proper. We just create a data structure in memory capturing these traces. So we track the execution flow of the tasks on the fly. And we exploit the statistical similarity across different tasks at runtime in order to determine two types of anomalies. One is flow anomaly, So this is, I have come through the normal path, and then now I take an unusual other path, which could be going to an error statement, or could be going somewhere where I haven't really gone before. And second, performance anomalies for normal code executions that have abnormally long durations. So the prototype that we built, so we have an actual system in operation at the university. We interpose our own task execution tracker in between the server code and the log4j, so the logger code here. So we interpose ourselves in a very thin layer in between these codes. And the task execution tracker on each server node will track the log points encountered by that server, by the server code, by each task. Will capture a synopsis data structure in memory for the task execution flow, and will stream those synopses to a statistical analyzer that is centralized per cluster. So for a full Cassandra cluster, for all the threads, for everything, I have centralized all these synopses, which are supposed to be a few bytes. So they're supposed to be very small. So let's give a very short example. Again, the file transfer code that I showed you before. We're supposed to capture the fact that this file transfer starts. So this is a context. I have inserted the set context instrumentation as the first line there. You see I am capturing the fact that this file transfer is executing in thread ID 134. This is the start of it. I'm going to capture all the log points that this task encounters at runtime. Those log points, I'm assuming, that have been instrumented already with a unique log ID per log point, so that I don't have to log the whole text, I just need to log one simple ID. And finally, when this task ends, the synopsis looks something like this. So 133 is the unique ID for this. File transfer is the stage or the phase name for the code that executed. 3.5 milliseconds is the time spent between log point 1, and the end, so this point and this point. And the set of log points that was encountered as part of this task is L1, L2, L4, so 3 IDs. Okay, now the question, remaining questions, how do I insert this instrumentation? Okay, and one way is it's semi-automatic, and another way is fully automated, and I will show you the fully automated later on. So this is somewhat semi-automated. Here I'm leveraging the Thrift library that normally comes with any Java server code. And the Thrift library typically has one of two patterns. So one is the producer-consumer model, where a producer thread here on the left will enqueue a task for a consumer thread to take and execute. And essentially, I will put this set context instrumentation just after the DQ in the consumer thread. And the other, the dispatcher worker model, in which a dispatcher thread will dispatch tasks for worker threads to execute. And here again, I will look for a thread run in the worker thread process, and I will have to insert a set context with the particular method that is being run. Again, this can be done manually, or it can be done by source-to-source transformation. And the end of a task will be captured automatically because a new task starts on the same thread, or a garbage collection thread starts. So we have done this for all the three codes that I mentioned before, HDFS, HBase, and Cassandra. And the total number of stages are quite small. So the total code could be large, but the modules that we're interested in are, in Cassandra is the most, 78 modules, 78 stages. So finally, our model is built for clustering. So it's built per stage. So for each of those codes that we have identified, we build a model in which we have noticed that a lot of the threads are executing a common path. So here it is shown as 99%, 99.9% of the threads are seen executing the path L1, L2, L4. So this common path, executed all over and over by all threads, is considered normal. When we see a path that is unusual, so it's rare, we classify it separately. So in this case, the L1, L2, you see has been executed 0.1% of the time. And so this is an execution flow outlier, meaning it is rare. However, just because it's rare does not mean that we flag it as an anomaly. And I will tell you what an anomaly is. So an anomaly is actually a statistically significant increase of outliers. So we already classify what is normal, what is common versus outlier, and then we look for an increase in existing outliers. And that is flagged as an anomaly. And now for performance anomalies, whatever is normal, considered normal, again, we look at the duration. So here 99.1% of this code path executed in 1 millisecond, 0.9% executed 4 milliseconds, and again, similarly, we flag performance outliers as in a similar manner as statistically significant increase of outliers of performance time. So I will show you a short evaluation on Cassandra to get a good grasp of what I've been showing so far. We have evaluations on all three codes. We run the YCSB benchmark for driving Cassandra. This is similar to real-world scenarios. By the way, Facebook has Cassandra running in the background. And we stress the system in some way. And in this particular experiment, we are injecting a particular type of failure in one of the Cassandra nodes. So we run a cluster of 4 Cassandra nodes. The YCSB is the workload emulator that you see. All Cassandra nodes are streaming their synopsis to the statistical analyzer, which builds our model on the fly. And Cassandra, for people who know database systems, has the internal structure of the database system. So it has a buffer pool, which is in-memory tables, where it writes the data records. And just like a normal database system, whatever we write in the buffer pool, so any write to the buffer pool, to the in-memory tables, need to be reflected on disk. So this is disk. This is in-memory records of Cassandra. And before we actually write to the permanent record on disk, we have to write to the write-ahead log. Okay, so whatever write is put here, first needs to go to here to the write-ahead log, and only then needs to be percolated down into the reflection of the database on disk. Why? Do people know? Because later on, if we need to abort, so if we need to roll back, then we have the new value in the write-ahead log and the old value is here. Okay? So this is clear for all database systems, they all work like this. So what we do is we drop 1% of the writes to the write-ahead log, and only for part of the time. So insert this intermittent fault on one Cassandra node, an error on the write to the write-ahead log. Okay? So let's take a look. So this is the timeline. We insert this intermittent fault here between minutes 10 and 20. Here only 1% of the writes to the wall are being dropped, not all. Okay, so this is what I'm showing here, failing 1% of writes to the wall. And what we see in the error files, just running blindly with Cassandra as is, we see one input-output error here, sometime between this minute 10 and 20. And then the whole node crashes somewhere at the minute 45 with a fatal exception. And this is all we see. Okay? So from that information, you have no clue. All right? And sure, we could have looked through the logs and look at the statements, but again, it's terabytes of logs. So with our system, we actually superimpose context information on the errors. And we tell you which kind of errors there are. So in this, you see that we have two types of errors. Like I said, execution flow anomalies are plotted like this. And performance anomalies can also be plotted. They're not plotted here. We also plot errors. So right on top of this error, we have square, which is our, we also capture the error. Also, again, an error here with a fatal crash. But we also show persistent flow execution anomalies related to the table, okay? So which is the in-memory table. So we show that there are flow anomalies on the table, execution of the table method, and also on these other methods at this point in time, and they are quite persistent. We actually can show you the template that's associated with the persistent anomaly, flow anomaly, and this template is saying the mem tables are frozen. We can also show you the log statements, the sequence of log statements that are associated with that mem table frozen. And what is interesting here is to see that in our model, we captured the normal and the anomalous control flow. And you can see that the fact that the mem tables are already frozen is not enough in itself to tell you that an error has happened or it doesn't happen. Okay? Because in fact, you see the mem table is frozen in both the normal and the anomalous flow. So, in fact, this means that the mem tables have been locked. There's another thread potentially flushing them, as you can see over there in the full template message. And in the normal scenario, they will be unlocked, and we proceed. In the anomalous case, the tables are locked and they're never unlocked, and we're just stuck there. And it's unclear to us why Cassandra could not recover the error in that case that we caught. But what happens in the full system is we see the information from node 1 that I showed you before. Mem tables are frozen, persistent message. We see the other Cassandra nodes are being affected as well. So we see these persistent error messages percolating on the other nodes with a template hinted handoff timeout, which means Cassandra is trying to pass some of the requests that failed because the failed writes to the write-ahead log onto other nodes for re-execution. This summary, so this window that I'm showing here is actually a summary of 5.4 million tasks. Okay, so you see that the synopsis allows us to show you a lot of information in a short window that you would otherwise have a lot of difficulty seeing looking in the terabyte files. And you see that the error in this case is quite dramatic. So this is the throughput. So I'm not sure if you're seeing, this is the cumulative throughput of the whole cluster. And at some point, after these mem tables are frozen, you see the throughput dropping, and it actually never recovers. I mean, the Cassandra is trying to re-execute those requests, but never succeeds for some reason, and the throughput remains low. So it's a significant error. And again, all you would have seen, if it weren't for our context modeling, would have been this. And you cannot just figure it out from that, and you cannot figure out by digging through the logs and trying to make sense of it either. Okay, so we are using these methods in order to uncover bugs and misconfigurations in the codes I mentioned, Cassandra HDFS HBase, and we have found several bugs and misconfiguration in these codes, some which are running always. Okay, so for example, in HDFS, there's this empty packet bug that is normal, so the system runs with it normally. So it just shows intermittently, but the system runs as is with this bug in it. Okay. I was telling you about the overheads, so let's go back to that question. So what is the cost of our analysis? If you take the state-of-the-art system with regular expression matching and put it on the logs, so you have, for example, a Spark cluster with regex matching and you do offline processing. If we take, like, let's say a small amount of log data, 1.6 gigabytes, not the terabytes, this means 12 million log messages, and it means 12 minutes on an 8-core system that are fully utilized for the regular expression matching. For our solution, we use only 1 core. It's real time. We use only 3% CPU on 1 core, okay, for developing the synopsis and writing them out. Storage overhead is significantly reduced as well. So the 3 systems that I mentioned, HDFS, HBase, Cassandra, we have, if you enable verbose logging for these systems, like I said, you get a huge storage overhead, and with just our synopsis, which is enough for you to actually build that diagram that I showed and to look at them to figure out the analysis, we have up to 1,000 times storage savings compared to verbose logging. Okay, runtime overhead, we have no overheads compared to info logging, which is just very, very brief information, just the errors and start and end here and there. So this is for Cassandra and HBase, we have absolutely no or like negligible runtime overhead when using our technique versus just info logging. And we have an estimated 1 false alarm per hour. So this is estimated because, like I said, these systems actually do run with some bugs. And this is comparing the alarms without any fault injection with the alarm with fault injection. So you see there are some alarms even just with the system running as is. And we couldn't determine fully if those alarms were false or not. So, but the estimate is only 1 false alarm per hour. Okay, and this is false positives in terms of flow anomalies. So in summary, I have told you about our technique called Program-Aware Anomaly Detection, which the idea is we provide the context to the anomaly, and the context is 2 things. One is the code name of the module, the name, the stage, the phase, whatever of the program. And the other is the log points, so the control flow, the execution flow of the program that is associated with the anomaly. And our method is in real time, low overhead, those 3% CPU that I mentioned. So minimal runtime overhead, it's the same as info logging. Low storage cost, you don't have to log the verbose statements because we already know what is normal and what is not, or we have a good idea of what is not normal, and we log only synopsis instead of logs. And low processing cost, and also the user is pointed directly to the things that are anomalous, doesn't have to look through the logs to figure it out. Our system is portable, is evaluated on 3 distributed storage systems that I showed you, HBase, HDFS, and Cassandra. And I'm done with this method. I will just give you very few highlights of the second one, which is the Semantic-Aware Resource Anomaly Detection, and then I'll take some questions. So SARAD monitors resource usage per context. Instead of the logs, we look at the resource usage, not the textual logs. And just like before is Semantic-Aware, so it's tied to the context. The model building is another machine learning method, which is recurrent neural nets. So before we had clustering, now we have RNN. And the technique is based on wavelet matching. So the CPU, I showed you, it's like a time series or a wavelet. And we do dynamic time warping in order to match the wavelet, the normal versus anomalous wavelets. And if we have time, I'll tell you how we deal with false alarms. So in the system workflow, I won't insist, except that we have pre-labeled, again we pre-label the data with context, which is the representative workload type, and the phase under which the data, the monitoring data is gathered. We also can incorporate in this method some user feedback. So in case there are false alarms, we can correct by user saying if an unusual pattern is or is not an anomaly. There is like a seemingly complex control flow system workflow here, but what is to remember is that we have a database which remembers the wavelets that are showing the resource anomalies, and we memorize these, and we build representative wavelets, so one per context. What is the normal resource consumption for this particular context? And because, like I said, these things are pre-labeled, then we can later on match whatever new wavelet we see to the representative one to figure out if it's normal or not. So, like I said, we capture workload characteristics and phase names, such as, this pertains to an insert, a read, an update of Cassandra. These are larger contexts than the ones that I mentioned, the module names that I mentioned before. We feed this pre-labeled monitoring information to a machine learning system. We store this information, and finally, we classify it through using an RNN, recurrent neural net machine learning. Okay, this is some theory on RNN. It suffices to say that the RNN learns recursively by seeing wavelet after wavelet after wavelet of the same type of context. And if they're similar, it just refines some hidden state information about that wavelet. Okay, so it learns from the data. Okay, and using this model, we perform a prediction for the input that we next see. Okay, and we do training versus testing, and we keep refining the neural net. So the wavelet matching, which is dynamic time warping, looks at the similarity between the representative wavelet that it memorized for a context and the wavelet that it sees in the input. And when new data arrive, okay, we know the workload type from our semantic tagging, and we figure out the relation or the similarity between the test wavelet, new wavelet that we see now, and the representative wavelet, PI, which is stored in our database. And if they're similar, then we are close enough to a normal pattern. If they are sufficiently dissimilar, then it's an anomaly. Okay, so this is more on dynamic time warping. I won't insist. Again, we have an experimental evaluation using Cassandra for nodes. We have an OpenStack setup with 3 Cassandra nodes, head node and 3 worker nodes. We have, in this case, 2 virtual machines running 2 workloads. One workload is used as interference workload, so this workload is used as an interference workload. Is running a disk hog and is causing resource interference for this other workload. We have other types of disturbances in the system that are being injected. And this is sort of what I want you to take away. So here we show Cassandra runs repeated. So you see run 1, run 2, and so on. So we just repeat the same Cassandra run. In the Cassandra run, you see that it has a high CPU usage in the first phase, then a period of low but stable CPU usage, and then the pattern repeats. So the pattern repeats n times. By this time, our neural net has been trained. You see that we have a predicted wavelet, the black one, and this is a new test data. So this is a test run. So this is a new test data that we are feeding in. And you see that the predicted one by that time is very close to the test one. Okay, so now if we inject various anomalies, like in this case we inject a disk delay anomaly in Cassandra over here at the end. And this is again the prediction of the system. And then obviously the distance, which is computed by the dynamic time warping, the distance between this wavelet and this wavelet becomes high and the system detects it as an anomaly. Again, if we have resource interference with this wavelet being the predicted by training and this wavelet being the actual one, where the disk hog is gradually being made bigger and bigger and more disruptive, and in the last part of the run is being detected as an anomaly. And I have some more on how we deal with false alarms. I guess in this case, so we can have feedback from the user back to the system, either for false positive or for false negatives. In the previous work, actually, we were not encountering that many false negatives, or actually none. Here, we are encountering some. So incorporating user feedback, which is going back to the system, telling him, okay, well, this is actually a false positive, this is actually a false negative, we can improve the accuracy of our RNN. So from 120 runs, we had 15 false positives, so normals flagged as anomaly, and 10 false negatives, anomalies flagged as normal. And we incorporating user feedback, going back into the system, retraining, giving new data, we have reduced those false positives to 2, and there are no false negatives anymore. Okay, just very briefly on automated phase capture instead of semi-automated. So like we said, we need to capture when a phase or a stage changes in the code. So here, like I mentioned, this is one piece of code being executed. Actually, this is a load phase from here to here, and this other is something else, is an update phase that is executing. They have visibly different CPU usage, and it's very useful if we can capture these phase changes automatically instead of us going and instrumenting anything by hand or doing a source-to-source translation. And we actually do this. We are in the process of refining this last piece in our prototype by doing Java snapshots. So this is a raw dump of the Java thread, and you see various parts of the code that are being circled. And I'm showing them here blown up. So in the Java snapshot, we have thread ID, we have the thread name, we have the thread state, and we have the stack, the core stack, the thread stack trace. And so what we do, we periodically do Java snapshotting of all the threads in the server system, and we compact all of the information for all the threads. So here we have 2 threads with the state runnable, with the names such and such, with the stacks, including this kind of statements. And we aggregate all the information about all threads in a window of a certain time. And then we calculate the difference between windows in order to capture automatically a phase change. So this is our system in action. So here you see the phase changes captured automatically. So you see the similarity of 1, meaning between windows is exactly the same. And here where there's similarity drops, meaning there's a phase change, we detected there's a phase change automatically, and again here. So the starts of phases are indicated by stars, and we actually detect some changes that we did not expect. So there are some micro phases or some other changes which are either false positives or changes that are not completely significant at this time, but still the capture is significantly accurate, even fully automatically. So in conclusion, this concludes my talk. I have shown you 2 methods for semantic-aware, a solution for semantic-aware reliability. And what we're trying to do is to bridge the gap between a machine-centric, fully black box solution based on data mining or regular expression matching, which is the state of the art, and a human-centric, which is the old way. Human-centric, the user goes and pours through the logs and tries to figure it out. either language-based solution, which is maybe Watson, IBM's Watson solution. There are other theoretical or analytical solutions out there. And our system is bridging this gap. It's a real-time, on-the-fly system for data analysis, which puts the human into the reliability loop. So we cannot really do without the human, we believe. And the human is aided by machine learning, so it's aided, he or she is aided by machine learning methods or models built on the fly. And the key idea that I showed you is that we have semantically tagged models. So we tag with some context from the application or from the system. And the models are based on different machine learning techniques, such as clustering or RNN. But in all of these models, we associate either the log-based control flow or the consumption signal, the wavelet, with the model. Okay, so the workload pattern, the code, either the program code or the signal of the resource consumption with the actual model. Okay, so this is my team. Stelios, my collaborator, is also here. Is from here. So this is the other two PhD students working on this project. And I thank you very much, and I invite some questions.
Thank you so much for the very interesting talk. Are there any questions on the part?
Yes?
If I understand well, as part of what you are doing, you model program execution. Have you thought about applying this knowledge outside the error detection, for example, for system optimization as well?
Yeah, so that's a very good idea. So the other parts of my work or our work that I haven't talked about here is about performance modeling. And in performance modeling, we indeed use the same kind of context for modeling the performance of the system and the application. So for example, per query or per method, we determine the resource to performance models as well. So for example, if we're running a database query and that query needs memory and CPU and disk and network, we can give various quotas of CPU and memory and network, and we can build like a 4D or 5D or whatever multi-dimensional model of performance, giving the resources for the particular context. Okay? So in that way, we do exploit this, and that work has also been partly published and is in progress right now. It's very time-consuming because building this kind of high-dimensional model is very time-consuming, and we are having some success with it, particularly for convex models. So if you can imagine, like if 4D or 5D model, it could be having multiple maxima or something like this, right? And so if it has multiple solutions, then it's very difficult for us to answer like a what-if question or on the model, right? A predictive kind of question on that kind of model.
Related to that, if you are dealing with particular types of applications, like databases, for example. In databases, there are well-known behavioral patterns of the users. For example, sequentially, you observe how the user accesses the data, and you observe a sequential pattern of the user. Immediately, the system might exploit prefetching strategies in order to minimize the cost of block accesses per block. Those are some part, of course, you can have adaptive strategies as well. these things have been used in the past in databases, and if you are able to keep a model, a detailed modeling of the program execution, maybe also applicable to applications, higher level applications like databases. But yeah, another question related to what you presented here. I was not sure if you are also trying to determine what was the possible type of error that may have happened in the system. Do you have enough information to try to analyze something like that, or?
Yeah, so you are making several good points. So one is, I guess, to my understanding, right? So database systems, like very advanced systems, use a lot of optimizations and adaptation in their functionality, right? And is it possible for us to actually model that kind of advanced behavior? And in fact, even if the behavior changes, right? So that is a very complex part of this work. That for some time, the system may work without prefetching, and then all of a sudden prefetching kicks in, and my model is not as good as before because the behavior of the system has changed, or the application and system has changed. And we, what we do for that type of problem, we have an incrementally evolving model. So over time, the system builds certain models, but because there are changes, there are dynamic changes, it tries to incorporate the new change that it sees. So it detects that, okay, the change has happened. There's a significant difference between the behavior before and the behavior now, either as a hardware change or a software change or optimization. And it's trying to build, again, versions of models per context and per, evolving over time, so incrementally evolving. Using a transformation of the previous model into the new model, for example, curve fitting or those kind of transformations. And I guess there was a second question, right? About
if you were also concerned about trying to automatically detect the type of error that may have happened.
About the types of errors, right? So right at this time, we in the work that I presented, we have sort of a help, an aid for the user by doing those synopses and by capturing the context, and we reduce the overhead and so on and so forth. But we don't go and diagnose, okay, this error was of this type, and you're right about that, so this is a limitation of the current system. However, we are working towards that in terms of classifying the type of errors, like is it software or hardware? If it is software, is it related to the memory system or whatever it is related to, and so on. So we have some tree-based classifiers for detecting the likelihood of an error being software versus hardware, or which type of hardware, if it is hardware, and so on and so forth. So we have additional methods where, for example, we do a copy of a virtual machine. So there's a virtual machine in execution with a certain configuration, but now we can replicate it, we can do a copy of the virtual machine, and we can change it in some way in order to understand if the error is deterministically produced or not. And based on that, right, so if we give it more memory, does it still fail? If we, and so on and so forth, right? So that work is in progress. Obviously, it's more challenging than what I presented so far. We don't have like very good automatic full process of automation of the diagnosis and the root cause analysis in fully automated. Right now, it's mostly user-based. But we do have some beginnings of that kind of work.
Any other question? All right. Let me ask you, probably you mentioned that I saw somewhere that your method, especially the first one, the PAAD, works in real time. But I'm really wondering whether any of these methods can really perform in real time. I mean, you need to detect that your system has been compromised at the time this is happening. Can any of these methods support this type of detection, real-time detection?
Yeah, so that's a very good question in terms of, can we, with these methods, detect an attack, for example, right? Like a system being compromised, including by malicious attack, right? And right now, our work has been limited to normal systems running with bugs, potential bugs, or situations of hardware failing, which causes the software to fail, right? So we have not tested our system with protection against attacks. So it's not a security area that we are targeting mainly. We are targeting fault tolerance of normal systems. And so some of our assumptions are geared towards that. So for example, the clustering algorithm, we assume that the system, what is seen most of the time, is normal. Okay, if the system is compromised already, then it will run anomalously for a long time. And then our system in that case will mispredict that that compromised state is actually the normal behavior. Okay, so this type of work is not directly applicable to security intrusions and those more complex attacks that we normally see, right? So we do rely on the fact that the systems most of the time run normally and some of the time will have occasional faults.
Thank you so much.